So previously in this section 4.1 regarding lattice vibrations, we have solved the infinite chain of atoms, and we have limited so far to a one-dimensional case. And then in the previous lecture, we went to discuss a finite chain of atoms, and we found out that the solutions now become discretized as compared to the cases of having an infinite lattices. And this finding, what you just discovered, is nice because it really defines a new discrete oscillations that are present in our system, and these can be called as quasi-particles. So in essence, they are collective excitations of the lattice, and the terminology goes that these are so-called emergent phenomena, that they arise into the system due to the periodic nature of the system. And these collective atomic lattice oscillations are also known as phonons, to respect the fact that they seem a little bit like particles, so that they behave a little bit like particles, but are not in fact not particles, but they are quasi-particles, so that they arise from the periodic boundary conditions and discretizing the volume we're dealing with and the atomic lattice vibrations. And here we will briefly in this lecture talk of phonons a little bit more and their discretized nature. Especially we will be looking into the dispersive nature of the discretized energy states and compare that against a conventional uncoupled harmonic oscillator case. So this is what we will do in this lecture. So as we just previously saw, the periodicity of the problem, so we have a one-dimensional finite atomic lattice. This, when we solve the system, the equation of motion, we realize that the solution provides us the dispersion relation. This also tells us that now the k, the wave vector in the dispersion relation, it's not a continuous variable anymore, but it's rather a discretized variable. And what this implies to us is that first of all, the dispersion relation in itself must be discretized. So it's not actually a line as such, but it's rather a set of discrete points in the first Brillouin zone that are the energies. Admittedly, we tend to have an awful many of those vibrational states. So it does look really like a continuum of states, a continuous variable, the omega with respect to k, but in principle it is not. And subsequently, since the frequencies and the k's are discretized, then the energies of the system must also be discretized. And this is important when we are calculating other properties and variables based on the energies of the system. Because in that case, we should, in principle, instead of integrating, we should be calculating over the sum of states. And now things actually start mattering in these calculations, whether or not the variables in question are discrete or continuous. But more on that later when we are solving the Debye model and calculating heat capacities associated with lattices. Here, what we will be focusing on in this lecture is that we will look a little bit more on the energy states and their discrete nature. So, the ideal harmonic oscillator and the energy states for a ideal harmonic oscillator, the EL, and EL is an integer, the principal quantum number associated with the harmonic oscillator, and the energy ladder is of a form that we have L plus 1/2 term and times h bar times omega, where L is an integer. So if we have a quantum mechanically working oscillator, L is the quantum number, the principal quantum number of our system, and EL is the associated energy of this integer, the quantum number. An almost identical equation can be found now for our system that consists of n coupled oscillators. So now, and in order to highlight the difference, I'm denoting that the energies are EL, and then inside the argument we have K inside the parentheses. So this energy actually depends now on the wave vector K of the state. And we have a similar multiplier in the beginning, so we have L plus 1/2, And 1/2, of course, that's the corresponding to the ground state of the system. And then we see that this kind of quantum mechanical oscillator never has a zero energy as such, but there's always this 1/2 h bar omega energy associated with the quantum ground state. And now what is different is that we have h bar, the reduced Planck constant, times the dispersion relation, so omega k and not just the omega, where this omega k is, like I mentioned, the dispersion relation. And this is what we have now in terms of the energy ladder or in the energy states for our n-coupled oscillators. And now n, although it can be quite large of a number, it is not infinitely large. And this, because of the periodic boundary conditions, discretizes our system. So the energies EL as a function of k are now both discretized and they are also dispersive, meaning that the energy depends on the direction of the wave that is propagating inside the lattice. So the order of the k value. And here I'm plotting what this means in graphically, like looking at the energies. The integer L and the wave vector k are shown and in the A for a uncoupled oscillator system. And essentially these are or can be understood as the quantum numbers of our system. So we have the integer L that gives us the energy or is related to the energy, and the wave vector k tells us in which direction this energy quanta is propagating. And figure A shows the L for an uncoupled oscillator case. That's the usual case, and we see that the states are equidistant from each other in terms of the energy. So if we go from a given state to a next level, the higher state, or to the lower state, the distance in energy is always h bar omega. And now in the B figure, we have the case for the n-coupled oscillator system. And there we do see that depending on the actual k value, the energy ladders are slightly different. So for example, here for a given amount of k, we have this kind of energy ladder. They are equidistant in this for a given k, but when we go to a different k value, we see that actually, in fact, the energy states are not equidistant. And this is the difference that emerges into our system now due to the fact that we actually have a dispersion relation that relates the omega and the k to each other. So this is the difference that we have in our system now. And this is essentially can be understood that we have a lot of phonons, a lot of quasi-particles that can be residing in our system. And then they may have a little bit different directions where they are propagating, different k values, and then of course different associated energies. And I think I haven't seen this in textbooks, but this probably is the reason why we start having a lot of electron phonon and phonon scattering processes in realistic materials, because we start having lots of different possibilities that how much of energies are being transferred when different phonons are being scattered to each other. So because we don't have an equidistant simple energy ladder like this, we actually have something a little bit more complicated. And I think that because of this complication, we actually start seeing more processes such as phonon scattering processes when we generalize our math to be beyond the linear approximation. So when we have also nonlinear interactions in our system, so that we can have lots of different kinds of scattering processes in which the k value is slightly changed, so that the phonons are seen to be scattering around in our atomic lattice. But this is just my gut feeling on this matter. So this is what I wanted to say during this lecture. So we have briefly discussed of the discretized nature of phonons, and I have shown that the dispersion relation really changes the energy ladders and the ladder that we're looking at here when we have the system of finite n-coupled oscillators. I thank you for listening, and please follow with me to the final lecture on our section 4.91 next, where we will generalize our discussion from a single one-dimensional lattice into three-dimensional lattice. And that will be quite interesting as a generalization. And after that, we will proceed towards calculation of heat capacities associated with these lattices. So thank you, and please enjoy the day. Bye.